So welcome everyone to our 42nd Bioelectrodynamics webinar, which is an event organized by our team and supported by the IEEE, Czechoslovakia Section, particularly Engineering in Medicine and Biology chapter. And also this webinar is supported by the International Union of Radio Science. For the attendees, the current policy is that you are muted and with the video off. Nevertheless, don't hesitate to write in the questions even during the talk, and they will be then answered after end of the talk. And also there will be place for interactions in terms of if you want to ask the question yourself, I can also unmute you, and you can ask the question on your own. So the plan for our lecture is 45 minutes as usual, and also to let you know, we are now recording the meeting, and then it will be published in our YouTube channel. So today is my great pleasure to introduce Gyula Polónyi, who is from the University of Pécs, Hungary, where he did obtain his Ph.D. and master's degree in the physics. And since 2018, he has been a research scientist at the High-Field Terahertz Research Group. And then in 2021, he became the supervisor of the High-Field Terahertz Lab and in the Pécs in Hungary. He also serves as an assistant editor for the Journal of Optical Society of America, B, so now it's Society of Optica. And he also received several awards, for example, Ferenc György Memorial Award for Outstanding International Level Achievements. And also in 2024, the Doctoral Talent Award from the Hungarian Innovation Center in Nanjing in China. And as he's going to speak today, his interests are mostly in nonlinear optics, in terahertz spectroscopy, semiconductors, with some application also to bio directions. So with this, Gyula, please, the virtual floor is yours. I'm looking forward to your talk.
Thank you so much. So thank you so much for your kind introduction as well. My name is Gyula Polónyi, and maybe I wouldn't repeat what was already mentioned. My topic, and I would like to thank for the opportunity to present on this webinar. My topic is called Alternate Routes for High-Field Terahertz Pulse Generation and Applications. Briefly about what is this terahertz and what do we know about it, although I just find recently that I think you may be also aware about it, so I wouldn't speak about this in detail, but so the terahertz radiation is a part of the electromagnetic radiation between the infrared and microwave ranges, and since it is close to the electronic and the electronic region and the optically reached regions, then their properties are really beneficial for many applications. Here you can see the typical parameters of terahertz radiations in this field. And here is a typical spectrum of a single cycle terahertz pulse with a corresponding spectrum. Mostly it is generated by tabletop laser sources, and one of its properties, which is very good, is that its electric field is directly measurable by electro-optic sampling. Where can we use it? So intense pulses at the low terahertz frequencies of 0.1 to 2 terahertz are enabling tool for nonlinear terahertz spectroscopic, resonant, non-resonant control of matter, manipulation and acceleration of charged particles, like electron undulation, longitudinal compression and acceleration of relativistic electron bunches, And there was a proposal for hadron therapy as well. But beside particle accelerations, this low frequency part of the spectrum, if we can achieve high electric fields, then many other applications are available for us. For example, the ultra-fast change of the insulator metal state of vanadium dioxide by terahertz, or at the low frequency, the impact ionization of semiconductors or thinner tunneling are also possible with high fields. Although at medium terahertz frequencies, the organic crystals are the most widely used crystals for terageneration, although for the lowest parts, it is usually linked lithium niobate crystals, what is the most widespread one sources when they use tilted pulse front pumping, a technique which was proposed in 2002 by János Research, the lead of our group. And since of them, I think the highest energies or most of the labs use lithium niobate in combination with tilted pulse front pumping for high energy terahertz pulse generation. Even the highest energy, which was reached by this Chinese group with 40 microjoule pulse energies, was used with a Titan Sapphire high energy laser source and with the lithium niobate crystal in tilted pulse front pumping. The lithium niobate crystal is usually used since it has a really large nonlinear coefficient, high damage threshold, and a large band gap with the absence of low order multiphoton absorption. And we will see the advantage of it. Okay, but what is this optical rectification? So optical rectification is basically an intrapulse difference frequency generation, which needs femtosecond light pulses. And here the phase matching condition for efficient generation is that the group velocity of the pump should be equal with the phase velocity of the terahertz in the nonlinear material. So before this tilted pulse front pumping was invented, they used other crystals with much less efficiency. But what is this tilted pulse front pumping mean? So with a dispersion element like a grating, we can tilt the pulse front and then we can image it, image this spot on the grating into the nonlinear crystal. With this, we can achieve that although the group velocity of the pump is still faster than the phase velocity of the terahertz pulse, but in the pulse front direction, this group velocity will be less so that the group velocity could be slower down to the phase velocity of the terahertz pulse with appropriate pulse front tilting. So with this, we can be sure that the pump won't go off from the terahertz pulse, and we can have a continuous generation of this terahertz radiation in a prism shape nonlinear crystal. With this tilted pulse front pumping technique, it was possible to increase the conversion efficiency in lithium niobate dramatically. And in certain semiconductors, it was also shown that the efficiency could be increased as well. So these results show that the past 20 years of Terrace pulse generation. These blue rectangulars related to lithium niobate ones, the triangulars related to semiconductors, and the green circles related to organic materials. Okay, but we have to say that this pulse front tilting, although gave a lot to us in the past, although it has reached the turning point as achieving significantly higher pulse energies and conversion efficiencies, has become increasingly difficult. This comes from the large pulse front tilt angle, which poses challenges for applications and limits further increases in terahertz energy due to the reduced interaction length, the imaging errors at large spot sizes, and the limited interaction length between the pump and the terahertz. Because of this, we need something more than this if we would go further. Because of that, many groups are looking for alternative sources or alternative techniques in order to go beyond what we have. And one of these approaches was the reinvention of using semiconductors for terahertz generation. So previously, they used semiconductors in collinear phase matching. For example, zinc telluride was used with Titan sapphire lasers because it's intrinsically phase matched around 800 nanometers. And gallium phosphide was used with ytterbium laser systems at 1 micrometer. Although they are less efficient, they were less efficient because of the smaller nonlinear coefficient. So if we compare it with lithium niobate, even gallium phosphide is worse than zinc telluride for that. And the other, main problem with them is the strong 2-photon absorption at these pumping wavelengths, what I mentioned, at 800 nanometers and at 1030 nanometers, where this 2-photon absorption resulted in free carriers inside the materials, and the increased number of free carriers will absorb the terahertz radiation. So the after-all absorption will strongly limit the available pump intensity and the efficiency for terahertz generation. The solution for that would be if we can go for longer pumping wavelengths. But now another problem comes in that if we go from the collinearly phase matched wavelengths to longer ones, then we lost this phase matching, what I previously showed that the velocities should be equal. So for that, we would need this pulse front tilting thing again. But now we can use it at semiconductors. What we can expect from it? We made some experiments, and we used a zinc telluride prism. We pumped it at 1.45 micrometer wavelength, where we assume that the free photon absorption coefficient has a local minimum. And we saw that a conversion efficiency of around 0.05% what we could reach. And we also saw some saturation, which was observed and reported by others. This saturation caused by the free carriers was reported by others in this paper. So then after that, we go to even higher or even longer pumping wavelength to 1.7 micrometer. And we saw that not just the terahertz pulse generation, not just the terahertz pulse energy increased, but also the conversion efficiency to a remarkable 0.14%, with pulse energies of 280 microjoules with proper phase pulse front tilt. Fortunately, the necessary pulse front tilt for semiconductors are less than half than for lithium niobate. And for this, the pulse duration change during the pulse duration variation inside the nonlinear material during the propagation in case of zinc chloride and gallium phosphide are much smaller than in case of lithium niobate, as the dispersion is smaller. And this means that the interaction length could be even longer for these semiconductors than it was in the case of lithium niobate. So from this, we would think that we can compensate even the smaller nonlinear coefficient if we have long enough crystal and proper pulse front tilting. The other thing which is interesting, that since that maybe we can do some other developments in the introducing of this pulse front tilt. And I mean here this contact grating technology. What does it mean? So if we could realize a grating structure directly on the surface of the nonlinear material, then we can omit all the tilting and imaging optics before this setup. And we could have a rather simple terahertz source, which will provide at a certain wavelength the high conversion efficiencies and high pulse energies. So how does it work? By these grating structures, the pump pulses which enter into the crystal will be tilted by diffraction into the proper directions, and then we will have this generated terahertz radiation through this crystal. Here you can see the realized structure, and this was the zinc telluride substrate that we used with this manufactured area of it. The reason that that it doesn't seem that this area fits well to this bigger substrate, because although we ordered this zinc telluride crystal as a single crystal, when we oriented it, we saw that it contained many domains with different orientations, and this was this part which have the highest area of the same domain. So for this, this grating structure had to be placed into this space. The other thing that you can see are these horizontal lines here, which are not the structures itself, but it comes from the grating defects of this crystal. So during the growing of the zinc telluride crystals, microbubbles generated inside them, and when the etching occurs, or when the etching is so when we do the etching on this surface, this surface errors make these defects in the structure. And in this case, the 20% of this was completely unuseful for us. I mean, something which decreased the efficiency. Nevertheless, as the grating was done, we carried out some experiments with it, with an ytterbium pumped or ytterbium driven OPA, and here you can see the results of it. Now, with this source, we could have even higher pump energies of almost more than 3 millijoules, and we could have a conversion efficiency of 0.3% with the highest pulse energies of almost 4 microjoules. It is, and if we compare it with previous zinc fluoride terahertz sources, we see that the conversion efficiency increased at least 2 orders of magnitudes, and the pulse energy is more than twice of it, which was previously. But it wasn't just the only benefits. So we recorded the beam profile of this terahertz beam, which was focused down onto a pyrochem that CCD by a Teflon lens. And we see that in the vertical direction, there is just a slightly divergence or difference between the theoretically calculated diffracted limited spot size, but on the horizontal direction, the calculated and the measured size is technically identical. So these results experimentally confirm that the terahertz beam can inherit the low distortion or the distortion-free profile of the pump. And maybe this is one of the key advantage of this source. So we have higher efficiency, although at higher energies, although we use the pulse front tilting technique, but even we can have a uniform pulse beam profile, which can be really useful for the applications. So we previously measured the terahertz energy and the terahertz spot size, and with electro-optic sampling, we can record the waveform. And through these data, we could calibrate this signal to that from that we could obtain more than a 0.5 megavolt per centimeter electric field, which is actually which can be used for not just for linear terahertz spectroscopy, but for terahertz probe measurements as well. So for nonlinear terahertz spectroscopy applications as well. With first order autocorrelation, we could obtain the spectrum, and it was shown that this spectrum goes beyond 2 terahertz as well, almost to 3 terahertz, which is also a good characteristic. Our calculations show that if we use, in case of semiconductors, if we use longer crystals, longer nonlinear materials, then this conversion efficiency could be even improved. So we repeated this measurement with this pump source, but now we used a zinc telluride prism in tilted pulse from geometry in this conventional one, and we could reach 0.7% efficiency and 40 microjoule pulse energies at this 1.7 micrometer pumping wavelength, where only the 4 photon absorption was effective. But you can also see that the efficiency started to decrease after around 15 or 20 gigawatt per square centimeter, The reason for this is the 4-photon absorption, and with these curves we could estimate the 4-photon absorption coefficient of this zinc telluride crystal, which was the first value for published value of it. Later on, we did some more direct measurements as well in order to measure this 4-photon absorption coefficients in zinc telluride and in gallium phosphide as well. But during that time, this was the first published result for it. And you see that the conversion efficiency that we had are more than 1 or 2 orders of magnitude higher than previously, with increased terahertz energies. So now actually this plot shows the context of these measurements or these results. The empty simples belong to lithium niobate related experiments. These blue rectangulars related to and this one related to zinc telluride terahertz sources. And you see that there is a 2.5 order of magnitude difference between these two results. This green is related to another semiconductor, gallium arsenide, at a longer pumping wavelength. And you see that this is what we achieved with these experiments. We could breach these 2.5 orders of magnitude, and with this we could have efficiencies, conversion efficiencies, comparable with lithium niobate sources. Okay, so this is what we have. We still have much to develop and to have higher energies and efficiencies, but I think we are on a track with this. What does this mean? Our simulations, so we continued with simulations, how we can optimize the pumping parameters in order to have better sources. And one thing that we do is to change from zinc telluride to gallium phosphide, as although it has a smaller nonlinear coefficient, but even have a much smaller nonlinear absorption coefficient. Here is a 10 times multiplication related compared to zinc telluride or gallium selenide, and even its dispersion is in the terahertz range is much smaller. So it could be a good candidate for even better terahertz sources, and not just for this, but also because it is a cheaper material and easier to grow good quality gallium phosphides than to grow zinc telluride ones. So our calculations showed that if we would pump a gallium phosphide crystal around 2 micrometer, then in the pumping intensity range of 15 to 20 gigawatt per square centimeters, with pulse durations of almost 100 femtoseconds or around 100 femtoseconds, we can have really good terahertz generation efficiencies. And if we choose a proper phase matching frequency, then we can have monotonically increased terahertz conversion efficiencies with the crystal length, with which we can get even better results. So it is worthy to find out what we can have, and so now we currently working with a Canadian research group to whom they can fabricate grating structures into gallium phosphide source crystals. So they now working on this direction, we have a collaboration, and I hope so that in the near future we can publish something in this as well. The other direction where we go is to investigate more the organic terahertz crystal sources. They are really attractive because they have high hyperpolarizability, much higher than lithium niobate. And as I previously shown in one of the graphs, with organic crystals, it is easy to have around closely megavolt per centimeter electric fields and have high conversion efficiencies, and maybe even if the highest pulse energy not comes from organic crystals, but remarkable 0.9 millijoule was achieved recently from an organic crystal source. And they can be used in collinear geometry. On the other side, they are not so attractive because of their material properties, and one of their main properties, which defines that what would be the optimal pumping condition, is their refractive indices, which limits or which narrows it down that what pumping wavelength would be the most beneficial for these high conversion efficiencies. And for this, if I would go back to that slide, even here you can see that in many cases they used OPAs, like OPAs driven by tight tensor fire systems or by Iterbium laser systems. Actually, all of them are OPAs, or there is a Russian group who use chrome force a high energy chrome force ferrite laser, with which they can they have really high pumping energies at 1.4 micrometer, which optimally fitting for the properties, refractive index properties of, for example, dust or DSTMS or OH1 crystals. So one of their drawback is the wavelength, the special wavelengths what they need. The other is the low damage threshold. So these crystals are really sensitive ones, and for prolonged exposure, they show crystal degradation. And again, not again, sorry, but they have also several absorption peaks in the terahertz range, which will distort the spectrum, terahertz spectrum, what we can achieve. So maybe I will show some example for that. And if I said that it is hard to grow zinc telluride crystals, I would, or yeah, sometimes it is even harder to grow these organic crystals, even in large scales, which comes from the nature of this slow evaporation technique with which they grow these crystals. And because of these difficulties, they consider to be expensive materials. Yeah, so the difference between the terahertz refractive index and the group refractive index in the optical regime of these nonlinear materials will define the coherence lengths of the several crystals, and this will define the best wavelengths for it. Here you can see two crystals, dust and DSTMS, in collinear geometry, and you see here that so this contour plot shows that there is a region here which will be as let's say, dips in the generated terahertz spectrum because of the phase matching mismatch, and also there are other parts which suffer from the same. But if we know these characteristics, we can find what is the proper wavelength for each of these crystals. But if we do another other approach, so the organic crystals they are actually are good terahertz sources, and we see that the pulse front tilting technique was again a good technique for achieving high conversion efficiencies. Now, the idea comes that what if we can have the marriage of these two techniques, and what type of benefits can we expect from this? One of them is that if we can a little bit, so maybe we can add a certain range of freedom choosing wavelengths, because with this even we can go for longer wavelengths and achieve the phase matching by tilted pulse front pumping. If we can do this, then maybe we can also do, we will also have a longer coherence length at other wavelengths as well, not just these specific ones. And if we go for longer wavelengths, this means that we can get rid of from this multiphoton absorption, the lower orders. So as we go for longer wavelengths, then we can eliminate the lower multiphoton absorption, and the higher multiphoton absorption allows us that we can use that we can avoid the damages which comes from the increased absorption, and we can use higher pump intensities as well. In order to investigate this, I use this analytical solution for the spectrum of the terahertz, and in the following, so which accounts for both optical and terahertz wave absorption, as well as the non-ideal phase matching, while still assuming a non-depleted pump. So this is what we use now, and in the following slides we will provide details on the major components of this application, of this equation. First of all, there is this d terahertz, which comes from the nonlinear susceptibility of this material, this chi2. And in case of organic materials, the dispersion of this chi2 and consequently the dispersion of this nonlinear coefficient is technically 0. So it's flat in the terahertz frequency range, which was shown by experiments, and it is totally the opposite in inorganic crystals. So it is so we will assume that this will be constant. But another material parameters which are maybe more important are the absorption spectrums. For the terahertz range, you can see here these absorption spectra for two groups of molecular crystals. The high absorption group, where you see that this absorption goes well beyond 201/centimeters, and the low absorption group of this, you see that these absorption, that there are a few strong absorption peaks, several ones, and these will determine the achievable spectrum. So if we can, we should choose crystals with lower absorption. The other interesting parameter is the pump spectrum, which will determine the spectral bandwidth of the pump pulse duration. Shorter pulses have intrinsically broader bandwidths. Here we show the theoretical contour, which was supported by many experimental results. You see that as the Fourier transformation connects the pulse duration and its spectrum, then this major effect. And here you see that as we increase the pulse duration, you see that the generated terahertz spectrum will narrow down. Here you can see these absorption lines, or the results of these absorption peaks in the generated spectrums for these OH1 and HMQ-TMS crystals. And you can also see that if we would need spectrum which is around 8 to 10 terahertz broad enough, then we shouldn't go beyond 100 or 130 femtoseconds in pump durations. Yeah, so using this model, I investigated several crystals, organic crystals, like dust, TS-TMS, HMQ-TMS, OH1, BNA, and MNA. And even this relatively simple model reproduces experimental trends surprisingly well. For example, Vicario et al. Experimentally demonstrated that HMQ-TMS generates higher pulse energies at longer wavelengths when it was used at shorter wavelengths. So if you see that, so in these experiments, he goes from around 800 nanometers up to 1500, and you see that in this region one could have higher frequency components, which creates higher pulse energies totally. And the other example recently comes from Zhao et al., who investigated BNA crystals. So he pumped BNA crystals at several wavelengths, and he also saw that in this case, the shorter pulse durations were better compared to longer ones. Okay, so what I did is to change one parameter here in these equations. This Ng now changed to Ng over cosinus gamma, with which we take into account the effect of the pulse front tilt. And in these insets, you see that as we change the gamma, the pulse front tilt angle, then how does these spectra changes? From these, we will have a deeper look into this dust crystal. And you see here the optical absorption, and here the, oh, okay, I see that the time is really fast. So, okay, the absorption in the terahertz range and the optical range, these are the major parts which have effects on the generated spectrum. But you see that the spectrum seems to be tilted at longer wavelengths. And this dashed line shows a wavelength what I chose as a long enough pump wavelength to check if we can have better conversion efficiencies or better sources, better pulses. You see in this plot, yeah, so what this shows is that I divided the integration of the plots when I check this cross section of these plots at the collinear case, and when it is tilted with different pulse front tilt angles. Actually, in the numerator there is the tilted case, and in the denominator there is the untilted case. And I checked and I integrated both the stereo spectrums like these what I have here, and where this ratio was the highest, I chose that angle to be the best for pulse front tilting. And for M&A crystal, even a more pronounced improvement could be achieved. And if you would like to get rid of from this high or this complex tilted Pan's-Ron geometry, and we cannot have contact gratings from organic crystals because they are not hard enough materials, then we can use volume phase holographic gratings, where with dichromatid gelatins we can have these slant areas where the refractive indices are changed. And for this they work as a transmission kind of transmission gratings, and then we can stick them into these nonlinear materials. Even we can place refractive index matching liquid between the two in order to do not lose any diffraction losses or transmission losses. And based on our calculations in COMSOL, we expect diffraction efficiencies above 90% in all these materials at a long pumping wavelength. I choose this because this is the wavelengths of thulium and holmium lasers. So if we can have more convenient sources here, we can avoid low order multiphoton absorptions. We have high diffraction efficiencies, so maybe we can increase the conversion efficiencies for terahertz generation. And according to our calculations, in even a 6 times improvement could be achieved in M&A. Now I do not have so much time, and I'm sorry for going forward. Maybe the other topic that I wanted to speak about is this investigation of charge transfer processes in bacterial rhodopsin using Terahertz detection technique. But I don't know if I should if I start it. Actually, it is maybe around 5 or 6 slides.
Go ahead. I think this is definitely something that could be of interest. So
thank you so much, and sorry for this. So there is this molecule, this bacterial rhodopsin, which is a single protein of the purple membrane of Halobacterium salinarium, and which can be dried and oriented in a ITO substrate very well. And when this rhodopsin is illuminated by green light, then a proton transfer will occur, and this proton transfer will result in an electromagnetic radiation, which is in this terahertz region that we can detect very well. So so one can orient these dried samples into some substrate, and then some experiments can be done with them. These original experiments were done by Gyula Polónyi, János Research and their co-workers in 2008, where they used green light to illuminate this sample, and then they detect this terahertz waveform, and they provided some simulations which explains that this part comes from the proton transfer, the other parts comes from vibration modes, and so on. And this was the first observation of a coherent terahertz signal from a biological system. Recently, we tried to repeat these results, and we had some certain difficulties. Like first of all, we had to check that our detection system is ready for detecting really low signals. So we had a ytterbium pumped gallium phosphide crystal. We pumped this crystal with 0.5 milliwatts, so the generated terahertz was really weak. Even we cannot distinguish one signal from the noise. The spectrum was totally in noise, but 100 scans gives us some the average of 100 scans gives us something which could be useful for calibrate our system. So this was the terahertz signal from a gallium phosphide source, This is what Gyula and the others published in that paper, and order of magnitude was technically the same. Other difficulties were that these samples was easy to bleach out if we used prolonged exposure more than a day or so. So we designed and placed these samples into motorized rotation stages, which rotates for days long, many days long. And with that, we could avoid this bleaching out. The other thing that we do is to separate the experiments from the environment by boxing, and even we use the purged nitrogen to increase the signal to noise ratio, and with that we could also record some we could repeat that detection of this Terahertz radiation, and maybe that's all what he had up to now. Regarding the theoretical background, I would propose to find these papers that I just briefly pointed. So I think most of the information, if you will find this paper, it's a really good one, and I think many answers you can find for your questions regarding to this. Yeah, and thank you so much for your attention.
Thank you very much. Very interesting, both technically and also scientifically. Especially, of course, for us, the last part was I would say, most directly related to our interests. Also historically, our research team is just interested in understanding how biological systems can convert electromagnetic field to, you can think of it as a nonlinear active device, biomolecules under certain gradients of fields and so on. So this is really interesting. I have a couple of questions. Meanwhile, I'll have a look if are there any more from the attendees. So maybe the technical one, if I just start to understand who did what. So in the slide where you've been directly forming a grating on the zinc tellurium substrate, that was fabricated in where was it fabricated in your lab, or what was the? You are muted, Gyula.
Thank you. Yeah, so it was done in an English. Yeah, this Cytec Precision
Okay.
Ltd did it, or actually they provided this work to another company, and later on it was changed. I mean, later on we tried to repeat this with the gallium phosphide early on, several years ago with this company, but somehow the quality wasn't the same, and there were some problems with it. But maybe it is a good I mean, good hint to look for a company who could do something like this.
Mm-hmm.
I can also give the link of this Canadian group, Jean-Michel Menard and his group, who can do lithography on semiconductors,
I see.
like zinc telluride as well. And maybe in the future, we also, in the following weeks, we will also have a manufacturing device with which we plan to do something like this into lithium niobate as well.
Okay, I see. I was just curious because I've seen some details of the defects. So yeah. So if you were not involved in the process, maybe that's too technical question. I'm asking because we also do. We have also certain micro and nano fabrication processes available here in our institute. But yeah, in particular in our team, we do mostly film lithography, because we develop the devices which are on a substrate, and then we deposit the thin film metal, and patterning is done by direct laser writing. That's something which directly our group is using. So yeah, I was wondering like where these effects appear from. But I think that's not necessary. I'm just curious. But if you're not involved, then it's probably maybe too technical there. Okay. Well, obviously, I would have most questions probably to the last part, but maybe before that, I'm curious in general because we were just discussing today morning with our in a team meeting, well, in small team meeting we had. I don't know if you are familiar, but I was trying to look in the literature all around, but it's not. I couldn't find really much info. So I'm wondering, for these high frequencies, speaking, order of 1 terahertz or even actually for us, what is interesting with less than that, so 0.1 terahertz. What is the effective field strength for breaking down the medium so that so that you ionize it? I'm wondering how much first like air can sustain, but what is most important for us, how much field strength before it breaks down dielectrically the water can sustain. There are two different questions, but for us both are kind of matter because what we are doing currently, we're building a setup where we have a certain power delivered in pulses. We use something like several hundred nanosecond pulses in a pulse we have several watts, and then we guide it with our waveguides, and then we taper down the waveguide so that we intensify the field strength in our waveguide. So, and I'm wondering, if you can refer to certain maybe work which was quantifying what are the field strengths materials can hold in this frequency range particularly.
Yeah, so I think yeah, so what I know that I think for this we should go above a megavolt per centimeter electric field level. So below that, according to our experiments, we didn't saw any phenomena which close to what you mentioned.
Megavolts per centimeter, but we should be safe there. I think we are probably not exceeding that. But anyway, out of curiosity, so did you observe in your case like there was some ionization or material breakdown? Did you in certain under certain conditions in your case in your materials?
Not in our laboratory, but yeah. So we actually built and delivered a high energy terahertz source to ALI Szeged, and they carried out experiments with it. So it has more than a megavolt per centimeter electric field, and when it was focused down into samples, then some kind of damage or alteration occurred on their samples. I don't know what they investigated it, but it's significantly changed it.
Yeah, I see. Yeah, I can imagine. Okay. So yeah, I was wondering about now I've had the pleasure to speak with the expert on a high field strength of transfer generation. I just wanted to hear what's known in the community. And I understand, well, obviously the devices for generation would not work if they would undergoing breakdown its own. So you only have that if you furthermore focus the beams. Okay. Okay, for this bacterial rhodopsin, I'm looking to my notes. So these samples, who was preparing them? Are they coming from?
So yeah, so this. Yes, so the first, so the technique, how can one do this orientation was comes from these Hungarian groups. Actually, so actually, this retired professor, Géza Groma, was the one who, with his group, prepared the samples for us in the University of Szeged.
Yeah, they're from Szeged. Yeah, okay. Now I thought
So-
I thought that the connection might go went through where Tomáš found that
so
there was a lot
maybe
of bioelectronics being done there. So this is interesting. Okay.
you can ask, you can go and Aaron Sipos, maybe the one who plays a major role in these. So maybe we can change connections. I mean, I can send you his addresses and so on if you
Yeah,
are.
that would be helpful. Yeah, thanks a lot. Thanks a lot. So
Yeah.
yeah, there is, so conceptually, I was not aware of this. I'm actually, that's very interesting. So conceptually, what you see, you pump the bacteriotoxin film, it's probably dried film or kind of like that, I guess. And then it generates, basically it behaves as a nonlinear converter, which helps you generate in the terahertz field. I mean, this is probably not really that much cool for high efficiency and high power handling, but it's interesting what's the underlying physics right there, which is taking place. So I'm wondering, do you think that you require? I mean, I understand for detecting some signals at all, you need to have rather high input power, rather high. But do you think this is something? Okay, how to phrase it? Would this be happening if we just illuminate it by non-coherent lights? Think of sunlight.
Yes.
Both coherence properties and also the power, let's say intensity properties. So was this something which is happening, you think, naturally to the level that, I don't know?
Yeah, but the problem with that is the timing. I mean, yeah. So this is a really a fast process. So this terahertz passes in the picosecond range.
Sure.
And so here we synchronized the pump and the probe. So yeah, so in this case, we converted the 1 micron into green light by second harmonic generation, and we know, yeah, but actually it isn't necessary to use a pulse laser source for it. So one can use some other source of green lights. Just yeah, yeah, so one thing is that I think there could be so it could also saturate. So when all the protons are excited and so on, or pumped outside from the membrane, then we wouldn't see any source of radiation. So yeah. So again, the timing would be the key point here. So yeah, the excitation should be really matching
Fast.
time with the probe.
I see.
Yeah.
I see. I understand from the technological perspective, you want to have controlled pumps so you can synchronize your detection. That's absolutely clear. But also, I mean, as I understand from what you are saying about the underlying physics, yeah, if you would have a continuous illumination, then probably you would not have the continuous generation of, I mean, continuous illumination by external light would not bring you continuous emission probably. Anyway, I mean, it's interesting. Okay, it will be interesting. What is there, of course, if in a living system where you continuously have the flow of the protons back. So in that case, it might be. Anyway, so maybe if you go back to what was the effective the field strength of emitted terahertz radiation for these conditions? It's an arbitrary. Okay.
So in this case, it was around this. Yeah, almost. So this 5 times 10 on the
yeah, 5 kilowatts per meter.
Yes,
of course,
yes.
it's rather weak, and it's still, I mean, compared to let's say the field strengths we are using for telecommunications is still super high. Of course, this is in the regime of the pulse excitation, but okay, it's interesting. This is very interesting. Okay. So I need to go to the original paper. I'm really glad that you also brought attention to that. I'll see what what's in there. It could be interesting to see what's the suggested underlying physics, like where that mixing takes place and why is it in this particular fields, I mean frequency range. Okay, cool, very nice, very nice. Okay, I see, I'm looking, so there's some comment in the chat from Takshin Akalin. So anyone from the other attendees, any questions? Now we have the chance to ask beyond my questions. So I'm curious about the history. So these unpublished data, is it something more recent, or is it something you already did some years ago?
So technically, we did it maybe 1 or 2 years ago.
Okay.
For a grant, or I mean for a something for that, and it was stopped. Although I think there are still ongoing experiments with this in the ELI in Szeged. So maybe you can also, so I can also add some contacts with them to ask, whom we were in contact as well. So this was a collaboration with Geza Groma's group. Yeah, so maybe there are some additional developments.
Okay. Cool. Very nice, very nice. Definitely, it's interesting for us because we are also doing modeling here of the protein vibrational modes and identifying their spectral range. And we have recently one paper on vibrational modes of our favorite protein, the tubulin. It's part of the cell skeleton, and also we are just finalizing one paper we want to submit in upcoming days regarding other proteins and their vibrational modes. We never included some nonlinear aspects here in terms of the external perturbation, but it's really interesting. But this is also special. Bacteriorhodopsin is very special in that it's transferring charge. So yeah, it's interesting to see how this is actually modulated by the vibrational modes of the bacteriorhodopsin itself. So it's a lot of interesting physics and biophysics in there. Okay, cool, very good. So thank you very much. I enjoyed it a lot. I think also other people did. So thank you, Gyula. It was my pleasure
Thank you so much.
hear from you, and we'll stay in touch. And please, if you'll be so kind and send me the contact, might be very useful. Maybe we can find out in future some potential ways of collaboration. That would be nice.
It's fully fine. Thank you so much.
Okay, thank you.
Bye-bye.
So I thank for everyone for joining and listening, and for our speaker, Dr. Gyula Polónyi, for presenting his research. So thank you very much again.
Thank you. Bye-bye.
Have a good day.